Hi, we are going to talk about carbohydrates today. So carbohydrates are carbon-based molecules that are rich in hydroxy groups. Indeed, the imperial formula for many carbohydrates is very simple. It's just CH2O repeat unit. So literally, it's a carbohydrate. Simple how carbohydrates are called monosaccharides. These simple sugars serve not only as fuel molecules but also as fundamental constituents of living systems. For instance, DNA has a backbone consisting of alternating phosphoric groups and deoxyribose, a cyclic 5-carbon sugar. Monosaccharides are aldehydes or ketones that have 2 or more hydroxy groups. The smallest monosaccharides, composed of 3 carbon atoms, are dihydroxyacetone and G and L glycerides. So, the common carbohydrates. We have some very common monosaccharides and the simple monosaccharides with like 4, 5, 6, or 7 carbon items are called like tetrose, pentose, hexose, and heptose respectively. Perhaps the monosaccharides of which we are most aware are the hexose, such as glucose and fructose. Glucose is an essential energy source for virtually all forms of life. Fructose is commonly used as a sweetener that is converted into glucose derivatives inside the cell. They are the common sugars that we all see most frequently in our daily life, including glucose and fructose. D-ribose, as the carbohydrate component of RNA, is a 5-carbon aldose, as is deoxyribose, is the monosaccharide component of deoxynucleotides. And D-glucose, D-mannose, and D-galactose are bonded 6-carbon aldose. Note that D-glucose and D-mannose differ in configuration only at carbon 2. The carbon atom in the second position. So sugars that are diester isomers differing in configuration at only a single asymmetric center are aptamers. D-glucose and D-mannose are aptameric at carbon 2, and D-glucose and D-galactose are aptamer at carbon 4. Many common sugars exist in cyclic forms. So the predominant form of ribose, glucose, fructose, and many other sugars in solution, so as is the case inside the cell, are not open chains. Rather, so the open chain forms of these sugars cyclized into rings. The chemical base for ring formation is that an aldehyde can react with an alcohol to form a hemiacetal. For an aldohexyl, such as glucose, a single molecule provides both the pyrene, aldehyde, and the alcohol. So the carbon 1 aldehyde in the open chain form of glucose reacts with carbon 5 hydroxy group to form an intermolecular hemiacetal. The resulting cyclic hemiacetal is a 6-membered ring. It's called pyranose because of its similarity to pyrene. So similarly, a ketone can react with an alcohol to form a hemiketal. The carbon 2 ketone group in the open chain form of a ketone hexose, such as fructose, can form an intramolecular hemiketal by reacting with either the carbon 6 hydroxy group to form a 6-membered cyclic hemiketal or a carbon 5 hydroxy group to form a 5-membered cyclic hemiketal. So the 5-membered ring is called furanose because of its similarity to furan. The displication of glucose and fructose, like also referred to glucopyranose for glucose and fructofuranose for fructose, as shown in the Haworth projections. So in such projections, the carbon atoms in the ring are not written out, and the approximate plane of the ring is perpendicular to the plane of the water, with a half line on the ring projecting toward the reader. We have seen that carbohydrates can contain many asymmetric carbon atoms. An additional asymmetric center is created when a cyclohemiacetal is formed, generating it another isomeric form of sugars we call the anomers. In glucose, carbon 1 becomes as asymmetric center. For these sugars, drawn at Haworth projections in the standard orientation as shown in the figure, so the designation means that the hydroxy group attached to carbon 1 is on the opposite side of the ring as carbon 6. Means that the hydroxy group is on the same side of the ring as carbon 6. The carbon 1 carbon atom is called the anomeric carbon atom. An equilibrium mixture of glucose contains about 1/3 alpha anomer, 2/3 beta anomer, and 1% of the open chain form. The fructose ring form of fructose also has anomeric forms, in which alpha and beta referred to the hydroxy groups attached to the carbon 2 anomer carbon. So fructose forms both pyranose and fructose rings. The pyranose form predominant in fructose, that is free in solution, and the fructose from predominance in many fructose derivatives. Beta D fructopyranose found in honey is one of the sweetest chemicals known. The beta D fructofuranose form is not nearly as sweet, so heating can convert beta fructopyranose into beta fructofuranose form, reducing the sweetness of the solution. For this reason, corn syrup with a high concentration of fructose in the beta D pyranose form is used as a sweetener in cold but not hot drinks. So pyranose and furanose rings can assume different conformations. The six-membered pyranose ring is not planar because of the tetrahedral geometry of its saturated carbon atoms. Instead, pyranose rings adopt two classes of conformations termed chair and boat because of the resemblance to these objectives. In the chair form, the substitutes on the ring carbon atoms have two orientations. One is axials or equatorials. So axials bonds are nearly perpendicularly to the average plane of the ring, whereas equatorial bonds are nearly parallel to this plane. So axial substituents sterically hind each other if they emerge on the same side of the ring. In contrast, equatorial substituents are less crowded. So the chair form of beta D glucopyranose predominates because all axial positions are occupied by hydrogen atoms. Furanose rings, like pyranose rings, are not planar. So this conformation is called an envelope form because the substrate resembles an opened envelope with the back flap raised. So in the ribose moiety of most biomolecules, either carbon 2 or carbon 3 is out of the plane on the same side of carbon 5. So glucose is a reducing sugar because the alpha and beta isomers of glucose are in equilibrium that pass through open chain form. Glucose has some of the chemical properties of 3 aldehydes, such as the ability to react with oxidizing agents. For example, glucose can react with cuprine ion, reducing it to cuprous ion while hating being oxidized, like from the Cu2 plus to Cu plus 1. So monosaccharides are joined to alcohols and anomers through glycosidic bonds. The biochemical properties of monosaccharide can be modified by reaction with other molecules. These modifications increase the biochemical versatility of carbohydrates and enabling them to serve as single molecules, or signaling or facilitating their metabolism. 3 common reactions are including alcohols, amines, and phosphates. A bond formed between an anomeric carbon atom of a carbohydrate and the oxygen atom of an alcohol is called a glycosidic bond. Okay, specifically, an O-glycosidic bond, is a predominant when carbohydrates are linked together to form long polymers and when they are attached to proteins. In addition, the anomeric carbon atom of a sugar can be linked to the nitrogen atom of an amine to form an N-glucosidic bond, such as when nitrogenous bases are attached to ribose units to form nucleosides. Carbohydrates can also be modified by the attachment of functional groups to carbons other than the anomeric carbon. Phosphorylated sugars are key intermediates in energy generation and biosynthesis. So R1 sugar modification deserves a special note because of its predominance in metabolism. The addition of phosphoric group is a common modification of sugars. For instance, the first step in the breakdown of glucose to obtain energy is its conversion into glucose 6-phosphate. So several subsequent intermediates in this metabolic pathways, such as dihydroxyacetone phosphate and glyceraldehyde, they are all very common phosphorylated sugars. Okay, so that's all for today. Thank you for your attention.